Jet transition. Two planes, two different design concepts. Both of them optimized to fulfill the role for which they're intended. It is not easy in these times to specify the operational requirements and satisfy all pertinent questions in designing an airplane. Considerations like payload, including the number of passengers, weight of baggage, range, field length, speed, and altitude, will direct the designer in shaping the best airplane for the desired job. The reason for aircraft to have jet engines is simply the global transport requirement for speed and size. Only the jet engine can produce the propulsion qualities required to fly faster. The passenger appeal for a fast and comfortable travel has defined the pattern of the modern transport aircraft. Not only faster, the jet engine can fly higher at the best engine operating conditions that match with the best airframe operating conditions. The jet engine can produce the enormous power required to satisfy the demands of airframe size made by the modern transport environment, allowing the introduction of wide-body aircraft into the market. The consequences of the power plant installation of flying higher and faster are quite obvious. A jet airplane with handling qualities different from the turboprop. This video has been prepared to help pilots understand the basic differences between a propeller-driven and a jet aircraft. Of course, the turboprop aircraft has been chosen as the basic object of comparison with the jet, but the matter is also pertinent if a piston propeller aircraft is used instead of a turboprop. The information presented herein is properly addressed in the Embraer Jet Family Initial Training and during the familiarization of the pilot with the handling characteristics of these planes. But it is covered here in a systematic way to get a clear vision of what are the elementary differences between those two concepts of flying. It is quite appropriate to start discussing the flight handling by showing the significance of the turbine engine installed on the jets. Jet engine is actually a slang name of what is called gas turbine engine. The name is exactly what it says, a turbine engine that is operated by gas rather than steam or water. The gas, the air itself, which operates the turbine, is the product of the combustion that takes place when a fuel is mixed and burned with the air passing through the engine. The simplest gas turbine engine for aircraft is a turbojet. Air entering the front case in large quantities is greatly heated and accelerated by being burned with fuel. Then the results of combustion are exhausted through the rear jet nozzles. There are several types of gas turbine engines, namely the turbojet, the turbofan, the turboprop, and the turboshaft. And they differ basically on how the energy of the expanding gases is converted into propulsive force. In the turbojet configuration, the thrust is provided only by the high-velocity gases exhausting through the nozzle. No feature is added to achieve the propulsive force. In the turboprop engine, the exhaust gases from the basic turbojet engine are used to rotate a turbine that drives a propeller, which is responsible for imparting a relatively small acceleration to a large mass of air. Thus, the added propeller develops the propulsion force. The turbofan engine is much like a turboprop, except that the propeller is replaced by a fan with rotating blades and stationary vanes, actually a compressor of large diameter. The fan is enclosed in a duct. Part of the air entering engine intake, after being processed by the fan section, bypasses the central engine core and expands in a separate nozzle to provide cold thrust. The bypassing air is not burned with the fuel. In the Embraer regional jets, the air leaving the fan surrounds the engine for its full length, and it is discharged through the jet nozzle. In other turbofan configurations, you might find engines with short ducts, where the fan air is exhausted directly into the air, without being mixed with the nozzle air. Now, leaving the turbojet engine aside, let's compare the performance of the turboprop and turbofan engines. Turboprop versus turbofan performance. Because of the propeller reduction gearing and the intricate propeller governing feature, the turboprop engine is heavier and more complicated than a turbofan engine of equivalent power. However, the turboprop performance during takeoff and climb is remarkably greater than the turbofan engine as a result of the ability of the propeller to accelerate a large mass of air at low flight speeds. But check what happens with the propulsive efficiency in the chart and see what happens when airspeed increases. The propulsive efficiency of the conventional turboprop decreases substantially as airspeed increases above 300 knots true airspeed and is null around 400 knots true airspeed. While the turbofan engine produces power efficiently up to and above supersonic speeds, it is clear that at high speed required for transport aircraft, the propeller is quite unsuitable and explains to some extent why they were offset by the introduction of the turbofan engines. It is very important to observe the flight regimes found to be suitable for the turboprop and turbofan engines. Comparatively, the turbofan is expected to have its maximum performance at higher altitudes and speed, of course, than its turboprop brother. From the pilot's point of view, operating a propeller-driven aircraft or a jet aircraft bears some important differences. Operational aspects of jets and turboprops. The rotating propeller itself is responsible for various aerodynamic effects, especially when it is pitched or yawed, and during power changes. Let's see these effects now. Well, due to the direction of rotation of the propellers to the right, clockwise when viewed from the rear, and this configuration is adopted by most manufacturers, the spiraling slipstream strikes the fin on the left, causing a left turning moment about the aircraft vertical axis. This effect is perceptible at high propeller speeds and low forward speeds, and varies from aircraft to aircraft. Consider also the offset of thrust created by downward moving propeller blades developing more thrust than upward blade. This results in that the center of thrust of the left engine is closer to airplane fuselage center line than that of the right engine, because the right engine has a longer arm than the left engine. Another component of yawing force appears. Realize that when the left engine is inoperative, there is greater yawing force than if instead the right engine is made inoperative. All these effects make it urgent for the pilot to use properly the elevator and rudder to prevent all pitching and yawing forces created. And of course, all these undesired power effects do not exist in the turbofan aircraft. Its propeller slipstream simply does not exist. The critical engine concept has no meaning on turbofan aircraft because all the power effects we described are absent. Remember the critical engine? This is the engine whose failure at takeoff is more critical from the control standpoint. All power effects act on the aircraft, yawing it to the left if the left engine is made inoperative. The asymmetrical thrust generated by the right engine will add to the power effects, making directional control more difficult. So the left engine is the critical engine when both propellers rotate to the right. Propeller slipstream and drag. It is very good not to have to compensate for the slipstream of the propeller, but nothing is for free. If you remember that the lift on a propeller aircraft is greatly influenced by the lift generated by the propeller slipstream on the wing area, you will realize that it is possible to vary lift rapidly by simply reducing or adding power. A typical approach power-off stall speed can be reduced by 10% at full power, a feature that can be smartly used to overcome many last-minute mistakes. And you can't profit from this spectacular effect on the turbofan aircraft. No lift bonus is available because the jet efflux is discharged clear aft and does not pass over the wings. Moreover, just as the propeller produces lift, accelerating rapidly under some flight conditions, it can be used to produce drag. When throttles are set to idle, the propeller produces drag, that is, negative thrust. The higher the RPM, the higher the drag. On the turbofan aircraft, however, the only practical means of producing drag appear with the provision of speed brakes, sometimes also lowering the landing gear. Imagine now a fast, clean aircraft facing the embarrassment of losing speed quickly when entering the terminal area or on the landing flare. We're not going to leave you in doubt. We will discuss the solutions later in this video. Poor acceleration times. In a turboprop installation, increasing power results in the required thrust being supplied quickly, something about 2 to 4 seconds to quantify what we say. Unfortunately, the turbofan engine is not that fast in respect to acceleration times. Thrust demands departing from a normal approach thrust to full thrust can be achieved rapidly, but from idle thrust to full thrust, things are quite different and can take about 6 to 8 seconds. This value can differ from engine to engine, so the full 8 seconds is a reasonable value to keep in mind. This acceleration delay can be of intense importance, especially during approach and landing. If flight idle is selected following a high and fast excursion above the glide slope at the lower end, the delay in getting enough thrust to recover the aircraft from the dive can cause difficulties for the crew. The engine should be reduced to idle only when the need for an increase of thrust has been removed. So add the poor acceleration response of the turbofan to the lack of possibility of increasing lift rapidly and the potential danger of the power-off operation, and you have reached 3 ways in which pilots of turbofan aircraft are not as lucky as the friend with the turboprop. Together, these facts are far more than enough to distinguish and emphatically mark the difference in one of the most significant aspects of operation of our 2 good aircraft power plant installations, the approach qualities. Engine operational recommendations. Because of the reservability of producing lift rapidly only by accelerating the airflow over the wings, speed is not that critical in recovering from a high rate of descent in the turboprop aircraft. We can say there is some room for error because you can still correct the mistake if you notice it before the flare. In the turbofan, however, there's little room for error because increased lift can be gained only through increase of airspeed of the whole airframe, which cannot be ascertained, or increase of the angle of attack, as we will discuss later on. The recommendations to cope with the delay in acceleration are very important. With a little bit of anticipation, it is quite possible to maintain the aircraft stabilized on the approach so that neither a drastic increase nor a dramatic power reduction is necessary. During approach, thrust levers should stay conveniently advanced to allow engine acceleration in case it is necessary to gain airspeed. Similarly, if an excursion to high thrust has been necessary to cope with a high loss of speed, don't leave thrust up for too long, or the airplane will go too fast again. Reduce thrust fairly soon, and you will fly on the target stabilized speed again conveniently. More will be said later when we discuss the aerodynamic matter involving turboprop and turbofans. We have discussed the modern transport needs for flying faster. There is no doubt that this is the trend of the aircraft industry. Flying faster determines some important aerodynamic characteristics of the jet aircraft, which we are starting to discuss right now. Aerodynamics. The key word to the top-level high speed is drag. Speed can be increased by reducing drag. Let's get into the theory of the airfoil to see how it works, diving into the aerodynamic aspects of the jets. To produce lift, the wing must pass through the air in such a way as to accelerate the air on the top of the wing to a speed higher than the air passing under the lower wing surface. The difference in relative pressure will result in an upward suction, the lift vector. The greater the difference in the lower and upper surface airspeed, the higher the difference in pressure. Hence, the larger the lift vector. But watch what happens when we accelerate the airfoil to speeds near the speed of sound. The local speed on the upper surface is higher than the free airspeed, and it is quite clear that airspeed over the wing can exceed or be very close to the speed of sound, although the airplane is still flying at subsonic speed. At a certain speed, shock waves start to form on the wing and the compressibility effects become apparent. The speed at which the shock waves first appear is the critical Mach number. If speed is further increased above the critical Mach number, drag increases drastically. Buffeting is felt. Then the aircraft may suffer from certain stability and control deficiencies. The common sense signals that the jet should fly at the highest subsonic speed before compressibility effects, the shock wave we have mentioned, appear or become excessive. The exponential increase in drag must be solved with aerodynamic resources and design measures if we want to fly fast. Observe the conventional airfoil, normally used on turboprop aircraft, and then watch the supercritical airfoil, normally used in high-speed applications. The latter is characterized by very little camber in the forward portion. On the other hand, the rear portion is severely cambered. See what happens when forward speed increases. Both airfoils flying at the same speed. The shock wave appears first at the conventional airfoil and is delayed weaker in the supercritical airfoil. Hence, compressibility drag is delayed and weaker for the same speed. To reduce additional drag, jets have swept-backed wings. All is done to make the wing believe it is flying slower than it really is. Let's remember how, in a straight wing, airflow through the wing is really perpendicular to the leading edge. By sweeping a wing instead, the velocity vector has two components, one perpendicular to the leading edge and the other parallel to the leading edge. This latter component can be seen to have no effect on lift or drag, since the air flows along lines of constant elevation. The pressure distribution is affected only by the flow perpendicular to the leading edge, and it results in a component less than the chordwise vector. It is apparent that the free stream velocity can be increased over one wing without sweep. That is, the critical Mach number of a wing with sweep is increased over one without sweep. This is why a high-speed aircraft has swept wings. The consequences of having a low-drag, high-speed aircraft can be discussed now. Like everything else, when you take advantage of something, you've got to absorb the resulting disadvantages. No pain, you can handle it. The first consequences of a high-speed wing is that it has poor lift at low speed. Poor lift at low speeds. We have just demonstrated that in the swept wing, the speed component of the wing responsible for lift is lower than the real airspeed flown by the whole aircraft. Thus, lift is correspondingly reduced. There is no doubt wing sweep removes some basic lift. Check in the figure that idea. Observe that for the same angle of attack, the unswept wing produces more lift than a corresponding swept wing. Another way of interpreting this figure is that for a given amount of lift, a swept-back wing must be flown at a higher angle of attack than an unswept wing. Conversely, to produce the same relative lift, the swept-back wing requires more angle of attack. This slow response to changes in angle of attack means that things like a quick flare during landing are less likely to be successful in the jet aircraft. This poor lift aerodynamic matter is also of high importance in the way in which drag and lift vary with speed. The following figure shows how the total drag varies, comparing both the turboprop and jet aircraft. This shows a reduction down to low speeds, and then watch an increase with further reduction in speed. There is a point identifiable as the minimum drag point, which is the mark to identify the backside of the curve. That is, in the low speed range on the backside, reducing the airspeed actually increases drag. Flight on the backside of the curve requires you to take care with airspeed, not allowing it to reduce. In this region, drag increases faster than lift, and the end result is that the airplane begins to sink. Sink tendency may be corrected by putting the nose down and allow the airplane to accelerate above the minimum drag point. It's a quite unconventional maneuver and can rarely be used because it always involves height loss. You can also add thrust to accelerate the airplane, and a lot of thrust is required to overcome the drag and accelerate the airplane to gain altitude. This is valid for both turboprop and jets, with the exception that the speed at which this effect begins is much higher in jets. Moreover, in turboprop aircraft, this speed is well identified by the steepness in the drag curve, but it is quite flat, extended on the jet's curves. I just want to show you that if you allow the airspeed to decrease below the minimum drag point, the aircraft will quietly slide to the backside of the curve, and the jet does not produce noticeable changes in flying quality. Don't get caught by the situation. If you suspect you are entering in the backside of the drag curve, make a firm decision and simply add power with determination. Embraer does not recommend any approach with speeds other than those published in the airplane flight manual. Flying in the AFM speeds and keeping the flap maneuvering speed published in the airplane operations manual will maintain you in the safe region of the curve. Actually, flying the Embraer jets according to the rules gets you into the safe side of the curve. These aircraft have excellent handling qualities at low speeds. Yet, when compared to a straight-wing turboprop, there are differences. Obviously, pilots are supposed to fly at low speed for controllability reasons in a one-engine inoperative condition. But even if control is not a factor, it is very important that the low-speed end of the envelope be avoided to prevent a no acceleration, no climb situation from happening. And if it happens, the pilot must be aware that reducing speed will not increase flight path angle. Let me show you an important characteristic of the flight in high speed. Mach tuck. Observe the pressure distribution along the chord of a typical airfoil shown here in a subsonic speed and during shockwave formation. As the figure shows, the lift forces during shockwave formation act at a point nearer the trailing edge in relation to the subsonic flow, where the lift is predominant near the leading edge. If airspeed is further increased, shock waves move closer to the trailing edge. As it does, lift results. The more intense the shock waves are, the heavier the pitch-down tendency is. This can result in the aircraft accelerating rapidly to excessive high speed. It is a phenomenon referred to as Mach tuck. If an input to the elevator is applied to correct for the pitch-down tendency, the angle of attack is now increased. The shock waves are boosted, and the pitch-down tendency increases accordingly. It may happen in a generic aircraft that in transonic speeds, if the pilot pulls the yoke to counteract the pitch-down tendency, the increase in the angle of attack shifts the lift force in the wing so far aft to a point that the end result is inverted. The aircraft tends to pitch down further instead of recovering. The Embraer jet aircraft has been extensively flown to Mach 0.85, and no tendency like the Mach tuck has been observed. Recall the maximum operating speed is Mach 0.78, Embraer does not recommend any flight excursions beyond the aircraft operating envelope. Should an excursion out of the operating envelope develop for some reason, you ought to know that some pitch-down tendency might occur at speeds in the vicinity of Mach 0.85 and over. The mild tendency can be safely counteracted conventionally. That is, pulling the yoke will cause the aircraft to recover. As a general policy, recovery should be done first by changing thrust and drag, then by using elevator. All these recovery actions should be done as smoothly as possible, but not allowing the aircraft to accelerate to even higher speeds. Speed brakes may be used to increase drag. Embraer tested the use of speed brakes at speeds up to Mach 0.85, with the aircraft trimmed for Mach 0.78. An additional recommendation arises when using speed brakes at high speeds. Deploying speed brakes at high speeds induces a pitch-down tendency. The pilot force to counteract this tendency is 9 kilograms or less when Mach is 0.85. Higher counteracting forces may be required at higher Mach numbers. Therefore, using speed brakes will make you also pull back the elevator. The aircraft maneuvering envelope. We have shown how serious an excursion to extremely high speed can be. But we have also demonstrated that the Embraer regional jets have shown safe operating characteristics with inadvertent exceedance of the Mach envelope. Nevertheless, if you combine the fact that operators opt to fly at high speeds and high altitudes with the potential threat of gust upsets or inadvertent penetration in turbulence, you, as a prudent pilot, ought to be aware of how the aircraft maneuvering envelope works. This is a chart documented in the approved AFM, which shows the low-speed buffet induced by stall and the high-speed buffet induced by the shock waves. Also, you can get the normal load factor or bank angle to buffet at a given Mach number, or the altitude margin at a given Mach number and 1G. At a given altitude and weight, there is a low-speed and a high-speed buffet boundary. In the example shown, there is a certain range in which the airplane can operate. The low-speed buffet is supposed to occur at Mach 0.70. If the aircraft accelerates to Mach 0.80, high-speed buffet will set in. The higher the altitude, the smaller the speed range between high and low-speed buffet. The lower the altitude, the greater the speed range. And the higher the weight, the smaller the operating speed range. The load factor G has a similar effect. Increasing load factor, as in making a turn, restricts the operating range. Pilots should become familiar with the buffet boundaries and the combination of weight, altitude, and speed at which they operate in order to anticipate any inadvertent excursion out of the envelope. Imagine an exceedance of the envelope during a turn. It might be difficult to distinguish between the high Mach number buffet and the pre-stall buffet. The unwise pilot may not recognize he is flying in the low-speed side of the envelope and incorrectly add power to speed up the airplane. Such an error will actually not help and will make the situation worse. Some care is necessary to know the maneuver margins, and for good reasons. Take a look at the buffet onset envelope in your AFM. Get the low speed and high speed margins, and fly always in a speed coherent with those margins. The dihedral effect. Every pilot knows that yawing an aircraft also causes it to roll. This is valid for either type of aircraft. It doesn't matter if it is a turboprop or a jet, a straight wing or a swept wing. This is called the dihedral effect. You know, dihedral is the angle of the wing with respect to the horizontal line, as seen in the picture, which causes an interesting aerodynamic effect. If any bank angle is introduced, the consequent side slip causes the wing to roll back to wings level. This is caused by the aircraft sliding toward the lowered wing, which increases its angle of attack, while the other wing has its angle of attack decreased, resulting in a rolling moment and approximately proportional to the dihedral angle. Wing sweep also produces a rolling moment due to side slip, caused by the change in relative sweep of the left and right wings. Due to wings being swept in a high-speed jet, the effect is normally stronger than in turboprop aircraft. See how it works. When the aircraft is yawed, the inside wing is slowed down and the outside wing is speeded up, therefore unbalancing lift in each wing separately, resulting in aircraft roll. The outside wing produces more lift because it is effectively less swept, while the inside wing loses lift because it is more swept. This contributes to further unbalanced lift, and rolling is exacerbated markedly, adding to the actual geometric dihedral. Consequently, pilots must be aware that rapid application of large rudder displacements or rapid application of asymmetric thrust may create control difficulties. Rudder and asymmetric thrust inputs must be made carefully and smoothly. Care is also necessary to overcome the dihedral effect during uncoordinated maneuvers, such as during approach and landing with turbulence or crosswind. Stall characteristics. The simple task now is to answer how different is stalling a propeller aircraft and a jet. The difference lies in the planform of the wing. Compare the straight wing lift distribution with the swept wing lift distribution. Lift on swept, untwisted wings is concentrated on wing tips rather than the concentration at the root in a straight wing. Since the wing stall is started in the vicinity of the highest lift coefficient, the swept wing has a tendency to develop a stall pattern that begins at the tip. If an actual wing were allowed to stall in this fashion, aileron buffet would occur, and the wing would drop. No nose-down moment and very little aileron effectiveness would be felt. When sweep back and taper is combined in a wing, the tip stall tendency is further aggravated. The straight wing exhibits low lift at the tip and high lift at the root, which contributes a lot for favorable stall pattern characteristics, adequately signaled by the stall warning buffet, adequate aileron effectiveness, and the usual strong nose-down moment. There are several means of correcting the tip stall tendency. The Embraer jets make use of wing geometrical twist to decrease the local angle of attack at the tip. In addition, the airfoil section is varied throughout the span to an airfoil with delayed stall development. Another feature used in the Embraer jet family are those interesting vortilons installed at the wing tip. They delay tip stall even more, so the jets have full roll control throughout the normal operating range down to stick pusher speeds. The variable incidence stabilizer. There is one other important feature of flying faster I would like to point out. On a fixed-tail aircraft, flying at low speeds, the elevator needs to be commanded up. While flying at higher speeds, it needs to be commanded down. If the speed range at which our aircraft flies is too extended, considerable elevator deflection would be necessary, requiring large displacements of the control surface to provide adequate longitudinal control. The solution for this case is the introduction of the variable incidence stabilizer. The variable incidence stabilizer is quite effective because it can be moved to a large deflection, which for itself is a good reason to manage its operation with care. A mistrimmed takeoff may result not only in higher than normal forces, but also insufficient control authority with full elevator deflection. Therefore, before takeoff, set the stabilizer to the required setting according to the CG position. We have come to a point in our presentation where we have gathered fair knowledge to give a full treatment to one of the end products of this video: the recommended flight techniques to approach and land a jet aircraft. Just to recall what we have said till now, a jet may be worse than a propeller aircraft in the following ways: the poor acceleration response of the jets in low engine rotation, the poor lift at low speed characteristic of the jet, the potential hazard of flying at the backside of the drag curve, the absence of propeller slipstream in preventing stall and producing extra lift. Put all these facts together, and you will see how potentially more difficult it can be for the pilot of a jet when making an approach and correcting inadvertent errors. Developing high sink rates is a unique problem and represents a potential hazard in jet aircraft. However, with a proper understanding of these considerations, neither one of these tasks is difficult. Remember that basically, you need more lift to get out of the increased rate of descent and go back to the proper flight path. And you can get lift by increasing angle of attack or airspeed. To increase angle of attack, your airspeed must be acceptable, or the extra pitch will take you to the backside of the drag curve, and the resulting sink rate will be higher. The final solution is thrust, but it may take a lot of time, so this option is practicable only at a safe altitude. To keep away from the potential development of high sink rates, fly the stabilized approach concept. The stabilized approach. When the whole approach is properly controlled, the possibility of something going wrong is drastically minimized. Avoid power-off approaches. Recall the poor acceleration response of your jet aircraft and set power with judgment. Anticipate the need for more thrust should airspeed decrease, but don't leave power up for too long or the aircraft will go fast again. Keep thrust in such a value which allows the engine to accelerate to a higher RPM if necessary, and it is also good to keep the airplane in the approach path. In the Embraer regional jets, a typical target N1 is 60%, and if you keep it within plus or minus 5%, it will be good. Keep the airplane in a stable glide path, and remember that large changes in airspeed will require also proportionally large changes in power and attitude. Variations in the target airspeed must be kept within a range of 5 knots. Prior to reaching the outer marker, or at least 3 nautical miles away from the runway threshold, the airplane should already be configured for landing in a stable glide path with landing flaps and gear locked down. For a normal glide path of 2.5 to 3 degrees, the resulting rate of descent is about 650 to 800 feet per minute. Rates of descent in excess of 1,000 feet per minute should be avoided. The use of the flight director for ILS guided approaches and VASIS and PAPI for visual reference is recommended. If possible, avoid sidestep maneuvers at less than 3 nautical miles away from runway threshold. Plan the touchdown point at the 1,000-foot runway marker. Do not permit the airplane to float during the flare. Using a normal flare technique as the airplane approaches the touchdown point, reduce the rate of descent by increasing the nose-up attitude and slowly reduce engine power in order to achieve idle as the airplane touches the runway. Normally, a 2-degree or 3-degree pitch-up change is required to reduce the rate of descent during the flare. Flying the stabilized approach concept is a goal that sometimes cannot be reached due to emergencies or ATC requests. To give you support to fly at that desired concept, let's discuss some interesting approach conditions. Non-precision approaches. It is well known that non-precision approaches may have a minimum descent altitude, MDA, in which the aircraft is leveled off and maintained until one has visual contact with the runway. Once visual contact is established, the aircraft may descend towards the threshold, transitioning from a descent to a level flight, and from a level flight to a descent again on a short approach, bears the characteristics of a non-stabilized approach. With radio navigation equipment available these days, a descent path can be created with which the aircraft descends to reach the MDA at a point where, if the runway is in sight, the descent can be continued without interruption on a normal glide path towards the touchdown point. We do not mean to invent new types of approaches. What we mean is a more efficient and safer use of existing approach procedure. High-speed approaches. Those pilots who are used to fly into busy hubs know it too well. ATC often requests to maintain an above-normal airspeed during the arrival phase of the approach To prevent non-stabilized approaches from happening, here is a set of recommendations. Stick to your limits. Do not accept a request by air traffic control that you cannot comply with. Start with the idea that you must be stabilized on a 3-mile final. That means stabilized speed, configuration, and thrust. Once cleared to reduce airspeed at the pilot's discretion, do it immediately and quickly. Do not reduce speed slowly, because you may end up on a short final with high speed and reduced thrust. Follow on the animated profile a typical, well-timed high-speed approach. Select flaps 9 degrees at approximately 3 miles to intercepting the outer marker. Set gear down. Reduce power to idle. At 200 knots, ask for flaps 22 degrees. At 145 knots, ask for flaps 45 degrees. This is your landing configuration, which must be established at 3 miles from the touchdown point. Upon setting flaps to 45 degrees, adjust power to maintain at least VAPP and cross the runway threshold at VREF. Use the proper technique to touch down in the 1,000-foot landing area. Circling approach. Circling approaches are very demanding. They're often very tight maneuvers that may end up in very short finals at the wrong height and wrong speed that can induce the pilot to use power off, steep paths towards the runway. And to complicate the matter further, sometimes the runway is at the side opposite to the flying pilot, and he only sees the runway when turning into final, when it may be too late to make corrections. Therefore, the most important thing to be observed in a circling approach is to be at the right height and right speed when intercepting final approach. Follow these rules to get it. Plan ahead. Estimate how many seconds after passing a beam threshold you will extend the downwind leg. Estimate how much you must descend on the base leg. The crew must have the runway in sight at all times. If the flying pilot does not see the runway, the non-flying pilot must advise immediately whenever the aircraft is getting too far, too close, too low, or too high relative to the runway. If the runway disappears in the mist or in the clouds, a missed approach is mandatory. Never, ever let the aircraft climb out of the downwind altitude through the cloud ceiling. If that ever happens, a missed approach must be carried out. Minimize configuration and speed changes during the approach. Most important of all, if, when on final approach, the aircraft is found not properly positioned, never try steep approaches or too shallow approaches towards the touchdown point. And never, ever do it powered off. Windy approaches. High-intensity surface winds are usually accompanied by turbulence and gusts. The problem then is to have a speed margin capable of covering any drop of aerodynamic speed due to wind change. Wind shifting and changes of intensity may require thrust changes. However, these thrust changes must be done at the proper timing and magnitude, as we have discussed before. Remembering that jet engines respond slowly to acceleration requirements when compared to turboprop. Excessive elevator inputs must be avoided. Normally, larger elevator inputs are not required even in gusty approaches. Playing too much with the elevator will result in unsteady, unstabilized approaches. The Embraer regional jets were designed with a turboprop pilot in mind. It was designed to be safe to operate by pilots without previous experience in jets. And the end result is an aircraft that is simple to manage and that has excellent handling characteristics. In some aspects, it is even easier to handle than the average high-performance turboprop. Fly these planes and you will confirm that. We believe we have reached our goal of getting you, airman, a level of information very important for you to understand each part of a whole, somewhat complex environment. In the process of learning, sometimes it is necessary to break down, fragment the information given, and then study the parts the way we've just done. But information alone is nothing without practice. Gathering knowledge is useless if not put into practical terms. We have given information so that you can integrate it with your skills and you will be successful in the dynamic environment of the skies. Embraer wishes you a good flight.